Well, to better understand electricity, let's try to remember gravity. So let's say we had something that was really far away, infinity, and we wanted to bring it a little closer to say here. And here's the Earth, big planet, and let's give this thing a label. So there's the radius. This is radius r. And obviously there's going to be like a little bit of force pulling from this planet onto whatever, this little asteroid that we brought up here. Let's see. If we wanted to do that, then this would have done some work. And so it would do positive work to pull in this planet from infinity. Positive work. And then we can also say that delta U equals negative work. That's just kind of a common relationship. This is for gravity, of course. And this will always hold true, so let's try to remember that equation. And then we can also say that delta U is going to be equal to the integral from infinity to r. And it's not going to be too bad, though, because we just have our regular equation gmm divided by r squared, which is just going to be equal to negative g capital M little m over this r here. And that's just going to be the potential energy, or rather the work, that was required to pull this in. And so I know it seems a little bit complicated, but these numbers should be relatively familiar to us because just think about it. You know, this thing can do a certain amount of work to pull in this planet to there, and essentially that's what it is. I know these negative signs are kind of messing things up, but don't worry too much about the negatives. It's just the amount of work here. So if that's how it was for gravity, let's take a look at electricity. It's essentially just going to be the same. But now we have two situations, because we might have something that's positive or something that's negative. But in either case, we're going to move them up. So in this situation, this negative charge, let's put a negative charge here, down here, and we'll put a positive charge here. So that way, when this positive charge is pulled in, then essentially this thing has done positive work, because it's just sucking it in, right? So positive work. In this case, however, if we put a negative here and a negative here, then in this case, you would have to counter that work, and so you'd have to sort of like force them together, and so that will require work to push it in. So that's why we have these positives and negatives. It sometimes get very confusing, but again, let's just kind of think in terms of magnitudes here. I think magnitudes would be a little bit better to think about. In any case, this one is positive because the force is this way. So these things are attracted to each other, and so we have a positive force. But in this case, the force is negative, so you're going to get the arrow in this direction here. Even though that we're pushing it in, we have the force in that direction. So that's how we get negative work on that side. Here's the negative U, delta U is equal to negative work. And then again, we're going to have a delta U equals the integral from infinity to r here. And this is actually just going to be a little easier because it is just KQQ over r squared, which will simplify to a KQQ over R. This is capital R here. So yeah, I mean, this shouldn't be too complicated. Again, we're just kind of either letting two things sort of do their work and come together, positives and negatives easily do the work there, or we're forcing them together here because it's against the charge. Now, I have been mentioning work, but I've been labeling this as the change of potential energy. And that's because we have this relationship happening here. But let's also define work and potential energy, I suppose, in a different way. So we'll say delta work is equal to Q And that's basically the charge that we're playing with, and then we're going to go from the initial position to the final position across the electric field. So something has to move across an electric field in order to, this charge is moving through an electric field, essentially, is what's happening here. So the charge is just moving through an electric field, and if you think about it, here's KQ over R squared, that's the electric field, right? And then here's your Q, and it's just the same thing. So these two things are actually the same. That's crazy. And now, let's try to build a little structure over here. So I'm going to start with a positive charge here, and then I'm going to try to push another positive charge over here into this one. So that's going to require some sort of effort, right? Call this 1, we'll call this 2, and the work is going to essentially be combining 2 and 1. So, putting those two together is going to need that much work. Then, let's say that was already set up, and then we wanted to add in something over here, another positive charge. We're going to add that one in there. This is already set up, so all we need to do is consider, okay, we're just going to add that and that. The cool thing about work in electricity is that it's scalar, so you don't have to worry about vectors and stuff too much. You don't have to worry about, like, components or anything. You just kind of add these things up. It's really easy. So you're just going to think, okay, well, I just need to calculate the work from here and the work between these two, and that's it. And then we're just going to say W, and this is from 3 to 1, and the work from 3 to 2. We're just going to add those two together, and we're going to label this one 3. And then we're going to add one more over here, and this one is just going to be another positive charge here. But here, just going to assume that these 3 are already in position. No work has been done there, but we're just going to essentially, you could add up all of these works. So if you want to figure out the total amount of work for everything, it would be the total. So like that plus that plus that plus whatever we find over here. Essentially, you're just going to be adding this, this, and this. If it was only this one charge, then you just need the work from 4 to 1, the work from 4 to 2, and then the work from 4 to 3. You just need to add up the 3 works, and then you figured out how much work you needed to add charge 4 into this mess. And sometimes you don't even have to do any integration. This is the cool thing. Sometimes you can jump straight into the shortcuts, but it's good to have the long, complicated way to look at it, so you could do analysis, and then, like, okay, well, if you don't really know what the heck is going on, just figure this out, just integrate it, right, if you need to. Or you could just jump to the shortcut. If you really understand what's happening already, you can just use a shortcut if you can. Sometimes it's applicable, sometimes it's not, but here's the shortcut, because it's just going to be QE and then X minus X naught. This will work if the electric field is constant. This will just work because it's just E. But if you had an X in your variable in E there, we're going to do another sort of integration later where you have to have a variable in your E. We're going to see that happening. Well, then you can't use the shortcut. You have to do the actual integral. But if you have a constant E, then you can do a shortcut. So let's say I had a positive charge like this inside an electric field. And we want to figure out how much work was done moving the charge from here all the way over here. It turns out if you move perpendicular to the electric field, you do no work. So when you cross across these little dotted lines here, you do 0 work. Work equals 0 when you move in this direction. Okay, and this is along these lines. And that's really important because along any of these little voltage lines, these are voltage lines. Let's say voltage 1 volt there, 2 volt here, and 4 volt over here. As you cross through these voltage lines perpendicular to the electric field, no work is done. That's interesting. Okay, and as we go through the electric field, we actually have to do partial differentiation and stuff like that to figure out what kind of work we're doing, or partial integration, stuff like that. So we're going to figure out what the partial paths are a little bit later, but the idea is that these lines are going to be very interesting because that's going to be voltage lines we're going to take a look at in just a second. All right, so in order to make sense of the potential energy graph, First, we're going to take a look at this field line right here. This is the electric field going in this direction. And we know that the electric field is actually going to be pointing towards lower voltage. And then that means that the higher voltage is on this side, the plus V. And I'm going to sort of interchange voltage and potential kind of, because we know that the voltage here is also going to be leaning towards lower potential energy on that side, lower voltage, lower potential energy on this side, higher voltage, higher potential energy. And then we also know that a positive charge, if we put one here, it's going to be moving in this way along the electric field line towards the lower potential. But if I put a negative charge, then we know that that is going to go counter the electric field towards higher potential. Interesting. So now we can make sense of this graph over here, and I can basically put a positive charge down here, and I can ask myself, okay, well, if I put another positive charge somewhere around here, actually the positive charge would start here, then I know that the positive charge is going to want to move towards the other side and essentially just come down here. And if I put a negative charge into this thing, it would want to start down here and move its way up here. And so now we've kind of made sense of the potential energy graph. Now you might notice a little mistake later in the video with this potential energy graph and stuff. Just ignore that, as it didn't really make sense to me at first. This is the correct graph. Now it's pretty easy to confuse electric potential, which is going to be volts, and potential energy, because, yeah, I mean, there's kind of the same word, right? But if I make this equation, U minus EU naught is equal to Q, and then times delta V as well, then we can see that the potential is very similar to voltage. So let's say this Q was not there, then it would just say voltage equals voltage, right? But let's say I put the Q there. Now all of a sudden, what happens is you get potential energy. So essentially, the voltage is kind of like the measurement of the electric field. It's just like if something's just by itself, it will create an electric field, right? But if you put another charge there, all of a sudden stuff happens. So that's kind of what this is trying to say. All right. Now let's make some units very clear. We've got the electron volt, which is supposed to be 1.6 e to the negative 19 joules, and then we have this other stuff. Well, we got the electric field times the meters is going to be equal to volts. And this is kind of like saying, okay, so the measurement of the electric field at a certain distance. We're converting electric field to distance, and that's going to give us a certain voltage, or a certain strength of the electric field at a certain distance. That's kind of what this is trying to say, and this is going to be equal to joules over coulombs. We can also say newtons over coulombs is equal to volts divided by joules over coulombs, JC, and then we have J divided, that's joules divided by newton meters, which is equal to volts over meters. So just a couple of different conversion factors, just in case we needed to do that. So I keep talking about how voltage is a measurement of the electric field. So let's try to determine what the voltage is from the electric field. Well, voltage from E might be a little bit better, because sometimes you'll be given E as the electric field. So let's try to figure out what the voltage from E is. We would say the final voltage minus the initial voltage is equal to the negative integral, and the initial, the final, and then we've got the electric field here, the direction of the electric field, and then we have to integrate that across the direction that you're going. So you have to kind of do partial pass here sometimes. It depends. Sometimes you can simplify things down, but usually you have to do partial pass. So Vx, Vy, Vz, that's going to sort of correspond to Ex, Ey, and Ez. You kind of have to use those to figure out what the electric field is in each direction before you can integrate this stuff. But sometimes you can use a shortcut. So here's a shortcut. Delta V equals negative E, and then you would have X minus X naught. And this really works if the electric field is constant, then it's chill. You can use the shortcuts. If the electric field is not constant, you really have to do the integral, because you might have like a x squared over 2 thing happening. So you got to do that. Now for things like a point charge or a sphere, the point charge or the sphere, the voltage is pretty simple. We're just going to have V equals KQ over R. I mean, it doesn't really get more simple than that. We're also going to say, hey, look, zero voltage at infinity. We're going to put 0 voltage at infinity. All right, we're going to put that. So that way we know that if we're super far away, there's no electric field. And then if we start coming closer, there's going to be an electric field. So this is again for a point charge. This could also be for the surface of a conductor. Okay, so just kind of remember that the VQ equals KQ over R. You could also use VQ over R for some sort of shortcuts, like if you had a semicircle of charge that was all equidistant from this particular point R, you could also use that same equation. Or if you had a shell like this is a shell, and let's say you kind of knew the voltage. The voltage of the shell on the outside is the same as on the inside. So the inside is equal to the surface, the shell voltage. All right. So if you try to find the voltage inside, it's going to be equal to the voltage on the surface. You can use the same R, the same radius. So this is just kind of how we can use shortcuts for V equals KQ over R, some of the easier calculations of voltage. Another easy calculation is the dipole. And unexpectedly, yeah, so the dipole is going to be P equals QD, that's the dipole moment, right? And then we would just have this simple equation which says that V equals KP cosine theta divided by R squared. And what cosine theta is meaning is, let's say you had your dipole like this, that was like plus and minus, right? Here's the center of the dipole, and here is your point right here. Well, this is theta. So you just try to figure out what that theta is. If it's 90 degrees right here, then that's just going to be equal to cosine of 90 is 0. So, well, if you're at 90 degrees, then that's going to be nothing. So you kind of want to be like over here to get full potential. That would be 0 degrees, and so you get 100% of dipole strength. That's the dipole. Now let's say we wanted to calculate the electric field from the voltage. It might be a little bit more interesting. The electric field from the voltage. Well, let's say we had E was equal to the change of voltage, V minus V naught, divided by R minus R naught. And that's delta V over delta R. Say that. Or we could also do the derivative, so dV over dr. And if we're going to be doing the derivatives, remember the partial paths that we were talking about? This is the shortcut. Remember that sometimes you can use shortcuts, and that's the cool thing about this electricity stuff, is sometimes the electric fields are constant, and things are relatively easy. You can just take the shortcuts. But if the electric field's not constant, then you have to do partial differentiations. So you have to take partial paths. That means that Ex is going to be equal to, dV over dx, and then Ey is going to be equal to dV over dy, and then Ez is going to be equal to dV over dz. You just take the path and down each position and calculate it. And we're actually going to do that a little later, but so you can see how it's done. But yeah, I mean, this is just called partial paths. Partial paths. So we're going to try doing some of that soon. Well, numbers don't really help to visualize things, so I'm going to draw some pictures. Let's see, we had a point right here, and then we had a couple of concentric spheres like this. Well, as we know, if we have the electric field pointing this way, this is all going to be perpendicular to every point here along the way. it's going to be pointing outward. It turns out that at every other time that we have this going, well, the same stuff is going to be happening no matter what. So that's why when we have the point charge over here, it's pretty easy, kind of works out in that way. But essentially we're going to get simple, 4V here. And just keep in mind, it's always 4 volts around this entire circle here. Over here it'd be like 2 volts, 2 volts, and then that's the entire circle, and over here would be 1 volt in the entire circle. That's kind of, this is called equipotential surfaces. Equipotential surfaces. What that's essentially trying to say is constant voltage. So the 4 volts is going to be constant throughout all that entire surface there. Well, these are some more equipotential surfaces right here, a couple of planes, all labeled as 4 volts, 3 volts, 2 volts, 1 volt, that kind of stuff. We're going to see that the electric field is kind of, going through them like this. Okay. And, yeah, so you'd be thinking to yourself, okay, well, basically at this surface is going to be 1 volt, this whole thing. And, well, these other things are going to be 4 volts. Well, yeah, those are equipotential surfaces. It turns out that all these are, of course, perpendicular to the electric field. So, yeah, it's pretty simple stuff on the equipotential surfaces. So one of the most important parts about electric fields is that it's always going to be pointing towards lower voltage. That's probably the most important thing. E points towards lower voltage. And that'll help you figure out, well, which direction the electric field is in and which voltage is, how far away things are. So it's just questions answered. So this is really good. Now we can head into the conductors. It's really interesting because remember these 90 degrees that we were making here? Well, it's also going to happen with conductor surfaces as well. So these electric field lines are always going to be, first of all, pointing towards the negatives and away from the positives, but also 90 degrees to every conductor surface. So it's even going to like curve and stuff and go like this and be 90 degrees just to make sure that it's exactly when it touches over here. So it's going to come out like this, and do these little curvatures. So, yeah, this is kind of crazy how conductors are like that. And then, of course, on the inside, the E is equal to 0. So we just kind of remember that. And yeah, so this is kind of equal potential surfaces there. Now let's say the voltage lines were a little bit like this. So we're really close here and super far apart there. Then we would notice that, let's say remember this is supposed to be 1 volt all the way across, 2 volts all the way across, 4 volts all the way across, so it's the same thing over here, right? But over here, this distance is really, really small. So when we try to take, if we try to take E equals the change of voltage over R, this change of voltage and that change of voltage is the same, right? But this is going to be a really small distance. So therefore, we're going to get a high E from this. So this is going to give us a high E if the lines are really close together. And over here, because this distance is so great and we have the same change of voltage, then we're going to get a low E over here. Low E. And so when we have spread apart lines, it's low. When the things are really close, and we have a high electric field. In this example, I've got 2 points. This one right here, VA, and this one right here, VB. And we're just going to try to figure out what's the change of voltage if we have the electric field pointing in that direction exactly. We're going to try to figure out the change of voltage from here to there. We have to use partial differentiation, partial integration for this, really. Keeping in mind, okay, we know that if the electric field is going this way, then there is a voltage line right here, isn't there? So that right there is a voltage line. So if we cross this voltage line, we're not going to get any kind of change of voltage across that line. So well, we kind of know that. But over here we have another voltage line. We could say that's kind of going like this, right? And up and down right in there. So that's kind of the second voltage line. We just kind of want to figure out if we go from here all the way to there. It's mainly across only the x-axis that matters here. But still, let's do the integral across the y as well. We're going to start doing it like this. We'll say VA is equal to the integral from 0 all the way up to y. And then, of course, here's the thing. We want to do it because this is a variable electric field. It's EX. It's not just E, it's EX. So this time we have to plug in EX for our electric field, and we're going to integrate that over dy. And isn't that just what we're doing right here? Okay, so then we just go VA is going to be equal to, we're going to plug in 0 because right here this is x equals 0, isn't it? So, well, our integration kind of stops there. But, you know, we're going to basically add in the plus c at the end. We're going to keep track of that plus c because over here the voltage is equal to c. That's the voltage. That makes sense. This particular spot has a particular voltage. There really was no change because there was no change next, but it does have a voltage, which is what we have. We could set that to equal to 0 if we wanted to, but it doesn't really matter. So anyway, we have this constant. Now let's say if we go into the next position, which is VB, and we go VB is equal to the integral from 0 to x, and then here again we're going to plug in EX and integrate this across dx. So in this case, we get VB is equal to EX squared over 2. And then we get a plus C over here. And so if we wanted to figure out what VB minus VA was, well, obviously the plus C's would cancel. And so the only thing that you would get left is going to be, you know, just the integral from here to there in the across the v-axis. So across this x-axis right here. So it's pretty interesting how this works. This might have been one of the homework problems that we had. Now the next integration we're going to do is the line of charge, and this is for voltage at this particular point right here. So for voltage, for the line of charge, we'll use V equals K dq over R. And we're just going to make this real quick because it's going to go essentially from negative A to B. And we're going to have this K lambda situation happening. K lambda divided by, we can call R x squared plus y squared, or square rooted. And we've already done this integral in one of our other videos. But let's try to just kind of quickly do it again here faster. So x tan u is going to be the sub we want to use. And if we remember, we can draw this little triangle that will help us keep track of things. We have a u and a y and an x, and over here we have x squared plus y squared. And then we should remember that the answer to this integral after everything was like ln of v. And so that's going to actually equal to ln of secant u plus tan u. And now we should be able to just kind of quickly just plug these numbers in because it should be like square root of x squared plus y squared. This is for secant u, x squared plus y squared over x, isn't it? If we follow this right here, secant u is that over that. And then we could use the tan of u, which we already know is y over x. So we're just kind of quickly, you know, solving this little integral. And then we can do the limits of integration. We forgot the k lambda over here, but we'll put that in later. So then we've got from negative a to b, so integration limits. And so the answer to all of this should be something like v equals k lambda, and then you have the ln of square root of x squared plus y squared, and then you need to add b on the top, and then on the bottom side you're essentially just going to subtract b. So x squared plus y squared, and then minus a. You're going to subtract a on the side, not inside of the square roots. But that's going to be how we can do line of charge. This is a little bit more difficult. So these integrals can get pretty crazy, and yeah, I don't know. So this equation that we found here, this k lambda ln situation, this I'm going to call v line, because that's the v for the line of charge. But over here I've got a ring, and for the ring we're just going to skip the integration, but I'm just going to say that the v ring at point P, of course, is going to be equal to k lambda and then 2 pi r. It's just going to be like circumference, right? And then divided by r. This is for the ring at this point P. And if we had a disk, the disk, then we could say that this is equal to the k sigma 2 pi, and then we have a square root of z squared plus r squared. And then this is minus z over here. And so, yeah, this should be kind of a couple of the basic integrals that we can do simply here. There's going to be a whole lot more, but this should be the basics of voltage, and it shouldn't be too complicated. Hopefully this was a good video.